Hi everyone. Today we're looking at our lesson, what is a limit? So our learning goals for today, learning the meaning of the limit of a function in a graphical sense, learning about the limit from the left and the limit from the right, very important concepts in a graphical sense, and learning whether or not a limit exists from a graph. We're also going to learn to draw the graph of a piecewise function and then discuss limits and whether or not they exist at specific values of x. So before we get into that, we're just going to look at the idea of a limit again. We have talked about it a little bit when finding the slope of a tangent. But one way to think about a limit is determining the limit of a sequence. So we're going to determine the limit of each sequence. So we're going to imagine in A here that the sequence keeps going on forever. Okay, so there's going to be an infinite number of terms. So what is the limit of this sequence, or what is the sequence, what number is the sequence tending towards? So as you get to the 10 millionth term, there's going to be a 2 with a ton of zeros and then a 1. And then when you get to the infinite term, there's going to be a 2 with an infinite number of zeros and then a 1. So the limit of this series is 2. And that's how we would write it. Sequence. And then in B, you can see that the denominators are getting bigger by a factor of 5 each time. So as we get towards an infinite term in this sequence, it would be 1 over 5 to a huge power, which is going to make the bottom outweigh the top by a ton, which means that this sequence is going to tend towards 0. In C, we're adding a 3 to the decimal each time, so eventually we'll have 0.3 repeat, which is 1/3. So the limit of this sequence is 1/3. This one maybe looks a little tougher. We can see that we're always adding a 0 before that first 6, so by the time we get to the infinite term in this sequence, there's going to be an infinite number of zeros before that first 6, so the limit of this sequence is going to tend towards 9. And then for E, I'm going to put a little star beside E here. So the sequence goes 1, -1, 1, -1, 1, -1. So what's going to happen on the infinite term? Well, we could guess that it could be 1, it could be -1. People in the past have said 0 because it's halfway in between 1 and -1. But the fact is that we can't predict whether what the infinite term is going to be. So we say that the limit does not exist. So it's not tending towards a specific number as the terms keep going and going. So the limit does not exist. You may have heard that before. The next one, people familiar with pi or however many digits in pi can see that that is what's happening here. So the limit as we get towards the infinite term would be pi. And then this one, 3, 6, 9, 12, 15, 18, so we're going up by 3 each time. As we get to an infinite term, that the limit is going to approach infinity. You can't actually equal infinity, so we would say the limit approaches infinity. Okay? And you can never reach infinity, so really this doesn't have a limit, but you could think of it, the limit as being infinity. Okay, so now we're going to go on to our first kind of graphical sense here. So hopefully you can follow this. So look at the graph and evaluate the limit if it exists. So first of all, let's look at this little part here. So what does that say? That says the limit as x approaches 4. So when you see that, you want to say to yourself, the limit as x approaches 4 of x plus 3. So if you see here, this line drawn in the graph here would be the line y equals x plus 3. Okay, and then it says the limit as x approaches 4. So what does it mean for x to approach 4? Well, x's are always on the x-axis. So x can approach 4 from the left. Okay, so approaching 4 from the left. What's our curve doing as x approaches 4 from the left? Well, our curve is approaching, looks like 7 here. Okay. And our curve can also approach 4 from the right. Our x can also approach 4 from the right. So along the x-axis, we're approaching 4 from the right. What's happening to our curve as x approaches 4 from the right? From the right, our line is still approaching that same number, which we can count up here. 1, 2, 3, 4, 5, 6, 7. So we could say that the limit as x approaches 4 of x plus 3 is equal to 7. And we got that graphically. But you could also get it algebraically. And why this is so, so when we were finding the slope of a tangent, we often could not let h approach 0 because our denominator would approach 0. But here our denominator is 1. So we can let x approach 4 because our denominator is going to be remain 1. So as we let x approach 4, our limit approaches 7. So this is algebraic. And all we had to do was substitute because it was totally okay to let x approach 4. And this one we got graphically. Okay, so same idea here. So look at the graph and determine the limit if it exists. So this says the limit as x approaches 5 of the function, so shown in the graph, or at least part of this function is shown in the graph. The limit as x approaches 5 of x squared minus 3x plus 5 all over 2x plus 5. So again, let's look at approaching 5 from the left. So there's 5. So x is approaching 5 from the left. And our curve, as that happens, is approaching, it looks like 1 right there. Okay? And then as x approaches 5 from the right, our curve is, again, looks like it's approaching 1. So graphically, we would think that the limit as x approaches 5 of x squared minus 3x plus 5 over 2x plus 5 is 1. That's what it looks like on our graph. So let's look at this from an algebraic standpoint again. So the limit as x approaches 5 of x squared minus 3x plus 5 over 2x plus 5. So again, if I let x approach 5, I would be worried about the denominator approaching 0. Does that happen? So if x approaches 5, 2 times 5, that's 10. So our denominator is approaching 15, which is fine. So again, we can just let x approach 5, and that would give us 5 squared minus 3 times 5 plus 5 over 2 times 5 plus 5, which would give us 25 minus 15 plus 5 over 15, which would be, sorry, 10 plus 5, 15 over 15, which is 1. Okay? So again, graphically and algebraically, we got the same limit. Okay, our next question. Look at the graph and determine the limit if it exists. So the limit as x approaches 1 of x squared minus 1 over x minus 1, and there's a picture of it, so you notice it looks like a line, but it's got a hole when x is equal to 1. We'll talk about that and why that is a little later. But if we just look at the limit from a graphical standpoint, which is what we're going to do first, so we're going to look at x approaching 1 first from the left. So here's my x-axis approaching 1 There's the number 1 right there from the left. What's our curve approaching? It's approaching that hole there, which is at 2. And as x approaches 1 from the right, again, what's our curve doing? Also approaching 2. So even though there's a hole there, as x approaches 1, x squared minus 1 over x minus 1 is approaching 2. Approaching. Important word there. So it looks like our limit is 2. So there's our graphical sense. So now we're going to use algebra to determine the limit. And then I've written, explain how to get out of the trap. So this is going to be an important concept as we move forward with limits. In the second part of this first chapter of calculus, we're just going to be focusing mainly on limits, and getting out of the trap is going to be a big, huge thing. So again here, we can't just let x approach 1 like we were able to earlier, because if we let x approach 1, our denominator approaches 0. Division by 0 is not possible, renders our solution meaningless. So that's the trap. The trap is I can't let x approach 1. So how do I get out of the trap? Usually there's something we can do algebraically that will help us get out of that trap. In this case, if we look at the numerator, it's a difference of squares. So I could factor it to give me x minus 1 times x plus 1. And then I can exaggerate this x minus 1 in the bottom. That's a number. And these two divide out. So that's how I got out of the trap, because now all of a sudden my equivalent limit is the limit as x approaches 1 of x plus 1. And our denominator, even though we're not showing it, is a 1. So now I'm free to let x approach 1 because the denominator is 1. So if I let x approach 1, this limit becomes 1 plus 1, or 2, okay, which is the same thing we got graphically. Okay, so our limits agree, which is great. We got out of the trap by factoring. And then in C, this is kind of going back to grade 11 a bit, explain why the graph of the function y equals x squared minus 1 over x minus 1 looks the way it does, like a line with a hole in it. So if you go back to grade 11 functions, we wanted to simplify this rational function to make it easier to graph. We would first factor anything that was possible to factor. So the top again is a difference of squares. The bottom can't be factored. But then we also had to state restrictions on the denominator, because we never wanted this denominator to equal 0. So we would say, as long as x is not equal to 1. Okay, so x can never be 1, because if x was 1, we'd have 0 in the denominator. So after we state the restriction or any restrictions on the denominator, we can now cancel our divide out like factors. So we've simplified this rational function to become y equals x plus 1 as long as x is never 1. So this looks intimidating to draw the graph of. This looks fairly easy. It looks like a line, right? Line where the y-intercept is 1 and the slope is 1 over 1, which is our rise over run. So our slope is out front here, 1 over 1. But the only problem is this x can't be 1. So if you draw this line up here in our graph, we have our y-intercept is 1 right here, and then up 1 over 1, except for x isn't allowed to be 1. So even though we want to put a point there, it's a hole. But from there, up 1 over 1, up 1 over 1, up 1 over 1, and same reverse it, and we've got our line with a hole in it. And the hole in it is because x is never allowed to equal 1. Okay. All right, so some calculus notation here. The notation, the limit as x approaches a of f at x equals L is read, the limit of f at x as x approaches a is equal to L. And that L is the limit number? Okay, so question 4, consider the following piecewise function to evaluate the following limits. Okay, so we're kind of learning a new topic here, piecewise function. You can see why we might call this a piecewise function because it's in two pieces. Here's one piece is this horizontal line with a hole at the end. And then our second piece is this slanted line. Okay, and remember the definition of a function, you may or may not remember from grade 11, is that for every x value, there's only one corresponding y value. So the only place you might be concerned is along x equals 2 here, because it looks like there could potentially be two values, but this open hole means there is not a value there, and the closed one means there is. So there's still only one y value for x equals 2, and everywhere else you can see there's only one corresponding y value. So it is a piecewise function. Now this is the equation of that piecewise function. So it looks different. Instead of just saying f at x equals x plus 5 or something, it's got this little bracket here, and it says f at x is equal to 1, but then it tells you it's always 1 if x is less than 2, strictly less than 2, and f at x is always x plus 2 if x is greater than or equal to 2. Okay, so what does that mean? So if we look at this top branch here, use yellow highlighter here of the function. So here's 2. So being less than 2 is like all of these values over here. Okay, that's x being less than 2. And it says whenever x is less than 2, the corresponding y value is always 1. So if I wanted to say something like, what's f at -1? Well, -1 fits into this restriction, x being less than 2, so f at -1 is 1. F at -5 is 1. F at 0, which is also less than 2, is 1. So you have all these points that are always 1. F at -1, F at 1 would be 1. What about f at 2? Well, f at 2 goes to a different branch because you're not allowed to equal, for this top branch here, x is not allowed to equal 2. It has to be strictly less than. But there is such thing as f at 1.9999. You get my idea, as many 9s as you want. As long as it's less than 2, you're going to get a value of 1. And that's where this hole comes in. You can get really, really, really close to 2 from the left, but you can't actually substitute 2 in your function. But this hole shows that you can get infinitely close to 2. But at 2, there's a hole at 1, okay? Because once x equals 2, we're on to this second branch here. Oh, let me just highlight then this branch in yellow with the hole. So once x actually equals 2, we're on to this branch here. So for instance, f at 2, because I'm greater than or equal to, so I'm allowed to equal 2, is defined by this function, x plus 2, so 2 plus 2, which is 4. And that gives you this point right here, this filled in point here. I just showed in green, so 2, 4. And then I can think about f at 3, because 3 is also greater than or equal to 2, would be 3 plus 2, or 5. F at 4, 4 plus 2, which is 6, and on. So you get this second piece of the function. Okay, so some new notation here. This says the limit as x approaches 2, and then there's this little negative sign here. So what do you say to yourself when you see this? You should be reading the limit as x approaches 2 from the left. of your function f at x. The limit as x approaches 2 from the left. So approaching, here's 2 again, from the left is doing this, approaching 2 from the left. So approaching 2 from the left, what's my function doing as I approach 2 from the left? It's approaching this hole here with the value 1. So the limit as x approaches 2 from the left is actually equal to 1. And how do I read this? The limit as x approaches 2 with this little plus sign, superscript. And that is written, the limit as x approaches 2 from the right. So now we're going to approach 2 from the right. So that's approaching 2 from the right along the x-axis. What's my curve doing? So if I look up, I'm on the green branch now, approaching, as x is approaching 2 from the right, my curve is approaching 4. So the limit as x approaches 2, well, since the limit from the left and the limit from the right are not the same, we're not closing in on one specific value. So the limit as x approaches 2 of that function f at x does not exist. We can use the letters D, N, E, so we don't have to write out all 3 words does not exist every time. Okay, so then here we have a big idea for calculus. For a limit to exist, the limit from the left must equal the limit from the right. Okay, so that's our big idea there. For a limit to exist, the limit from the left has to equal the limit from the right. And then in mathematical terms, we're saying exactly the same thing, but with mathematics. So this says here, the limit as x approaches a of a function f at x is equal to some limit L if the limit as x approaches a from the left is equal to the limit as x approaches a from the right is equal to that limit L. Otherwise, the limit as x approaches a of f at x does not exist. Okay. So here's another question. Karen drew the following piecewise function, y equals f at x. Use her drawing to evaluate each limit if it exists. So the limit as x approaches 0 from the left. So here's 0 in my crosshairs. I'm approaching 0 from the left. My curve looks like it's approaching 3 from Karen's picture. B is the limit as x approaches 0 from the right. So approaching 0 from the right. Looks like in Karen's curve again. Again, she's approaching 3. And then just the limit as x approaches 0, since the limit from the left and the limit from the right are both 3, then the limit as x approaches 0 is also 3. Okay, so our next one, the limit as x approaches 1 from the left. So I'm going to use red pen here. So here's 1 from the left. So if I'm approaching 1 from the left, what's my curve doing? So I'm looking at this branch here still. So as x is approaching 1 from the left, my curve looks like it's approaching 4. How about when I'm approaching 1 from the right? So here's 1, x, approaching 1 from the right. Now I'm on this piece of the curve, and it's approaching this hole, which has a value of -1. So then it says, what's the limit as x approaches 1 of this function? Well, the limit from the left and the limit from the right are different. So this limit does not exist. DNE does not exist. Okay, so now we've got a picture of a more complex function. We're calling it g at x this time. It's a piecewise function again. Make sure it's a function, so for every x value there's only one y value, so -2 might be alarming, but here's the y value and there's a hole here, so there's only one corresponding y value. At -1 we've got an open dot and a closed dot, so we're still got a function. At 2, same thing, closed and an open, and everywhere else. So for every x value there's only one y value. We've got a piecewise function here. All right, so the limit as x approaches -2. So here's -2 from the left. Means I'm going to be on this piece. So I'm going to be approaching, it's like 4. The limit as x approaches -2 from the right. So as x is approaching -2 from the right, my curve is also approaching that hole again from the right, which is at 4. So the limit as x approaches -2, since the limit from the left and the limit from the right are equal, then the limit as x approaches -2 exists and is 4. D, notice how there's no limit here. It's just asking what's the value of this function when x is -2. So when x is -2, the corresponding y value is here, and if we look across, that's 2. So g at -2 is 2, even though the limit from the left and the right are 4. And that's definitely possible when you have these piecewise functions that have holes. All right, so the next one, limit as x approaches -1 from the left. So approaching -1 from the left would be here. My curve is approaching +1. And then we have approaching -1 from the right. This time I'm going to be on this lower portion of the curve. I'm going to be approaching -3. And then just the plain limit as x approaches -1, since the limit from the left and the limit from the right are not equal, we say the limit does not exist. And then it's asking, what's the value of the function g when x is -1? So when x is -1, the corresponding y value is where there's a point, is -3. It just asks, what's the limit as x approaches 2 of g at x? So you have to do all that thinking. So the limit from the left, so if this limit were to exist, the limit from the left and the limit from the right would have to be equal. So let's kind of do this analysis. A lot of you will just be able to look at it, but as x approaches 2 from the from the left, I'd be on this piece of the curve, approaching -1. And as x approaches 2 from the right, though, I'd be on this top piece of the curve, approaching +2. So the limit from the left and the limit from the right are not equal, so this limit does not exist. So it shouldn't really have an equal sign there. And then it wants to know what's the value of the function when x is 2. So when x is 2, the corresponding y value is where the closed-in dot is, so it's -1. And then same thing, limit as x approaches 3 of g at x. So as I approach 3 from the left, I'll be on this part, approaching 5. As I approach 3 from the right, I'll be on this piece, again approaching 5. Limit from the left and right are equal. So the limit as x approaches 3 of that function is equal to 5, exists and is equal to 5. Okay, number 7 here. So we are going to draw a piecewise function. So sketch the piecewise function. F at x is equal to, so x squared when x is less than or equal to 1, and -x plus 3 when x is greater than 1. Okay, and then after we've drawn after we've drawn our piecewise function, we'll discuss some limits. But first of all, let's focus on drawing it. Okay, so let's focus on this first branch here. And stuff happens at x being 1. So first of all, we would kind of ask ourselves, for this branch here, are we allowed to have an x value of 1? Yes, because it's less than or equal to. So I could just, what's f at 1? It would be 1 squared, which is 1. So there's a point, a closed-in point. And then anything less than or equal to, so we could try f at 0 is going to give me 0 squared, which is 0. F at negative 1 is going to give me negative 1 squared, which is 1. F at negative 2 is going to give me negative 2 squared, which is 4. And probably a lot of you recognize x squared as a parabola, but it's only for less than or equal to 1, so we can draw it in fairly confidently knowing it's going to look like that. Okay, so this is our kind of our yellow portion of the branch here. We've got a filled in dot. And there's one piece of our piecewise function. The next piece is for when x is greater than 1. So again, we're not allowed to have x equal to 1 here, but we could have like f at, if you want to think about it, so just a little bit more than 1, 1.01 maybe. We'd get negative 1.01 plus 3. Which is 1.99. So, and as we keep these 0, 0, 0, 0, 0, 1, we're going to get closer and closer to 2, which means at 1, we'll have an open hole then around the y value 2. Because we're not actually allowed to put 1 into the function, but we're allowed to put something just a little bit greater than 1. So you can imagine putting 1.000000, infinite number of zeros, 1, and you'd pretty much get 2. So we have an open hole at the point 1, 2. But then I'm allowed to put anything into this branch that's greater than 1. So f at 2 is something easy. So that could be negative 2 plus 3, which would give me negative 1, or sorry, positive 1. And then I could do f at 3. Negative 3 plus 3 is 0. F at 4. Negative 4 plus 3 is negative 1. And then I can draw that branch in. And that's my green branch. And it's got an open hole, and then it's a straight line with a slope of negative 1. Okay? And if this was just the function, then its y-intercept would be at 3, which you could see, but we're not allowed. X can only be greater than 1. So that's what our piecewise function looks like. And then this is 1 here. Okay, so first question says the limit as x approaches negative 1 from the left. So approaching, here's negative 1 from the left. Our curve is approaching positive 1. The limit as x approaches negative 1 from the right. We're still on the same yellow part here. And again, we're approaching 1. So the limit as x approaches negative 1 exists and is 1. Now we're looking at the limit as x approaches 1 from the left. So here's 1. From the left, I'm going to be on this yellow portion of the curve, approaching this filled-in dot, which is 1. As I approach 1 from the right, though, I'm going to be on the green portion of the curve, approaching this hole, which is at 2. And so then the limit as x approaches 1, since the limit from the left and the limit from the right aren't the same, it does not exist. So there's a question where we had to draw the piecewise function and then answer questions about limits. And same with our last question here for today. Sketch the graph of f at x equals, this is a 3-piece function, so we're really getting into our piecewise functions. And it's defined to be negative x minus 2 if x is less than or equal to negative 1, plain x when it's between negative 1 and 1, and then x squared, so parabolic, x squared minus 2x for when x is greater than or equal to 1. So let's focus on the top part first. So x is less than or equal to negative 1. So here's negative 1. And we are allowed to equal negative 1. So f at negative 1 is going to be negative 1 minus 2, which is negative 1. So negative 1, we have a filled in dot there because we're allowed to be negative 1. And then f at negative 2, because we want to be less than and equal to negative 1. So it's going to give me negative 2 minus 2, which is going to be 2 minus 2, which is 0. And then f at negative 3, negative 3, which is 3 minus 2, which is 1. And once you've convinced yourself that's going to be linear with a slope of negative 1, you can draw that part of our curve in. And it's going to go on in that direction as we get more negative. So we've got a closed in dot. Here's our yellow branch. Okay, so our second part, doing green here, is for x's between negative 1 and 1. So, x's that are greater than negative 1, so we can't be negative 1, but we could be like negative 0.99999. So if you think about that, f at negative 0.999, well, it equals negative 0.999, okay? Because it's f at x equals x. So that's pretty much negative 1 again, right? Negative 1. There would be an open circle here, but because it's already filled in by this upper branch, or the branch before it here with a closed dot fills in open dot. Closed dot fills in open dot. So if they're in the same location and there's a closed dot, it fills in the open one. Okay, so we don't actually have an open dot there. It was filled in up here. Okay, and then we can have any number between negative 1 and 1. So easy one that comes to mind would be f at 0 is 0. If you wanted f at a half, it would be a half right there. Then what happens at 1? Because again, I'm not allowed to have 1 in, but I can get really close to 1. So I could have like f at 0.999 again would be 0.999. So almost 1, but not really allowed. So I have my open circle there. And then I can join the part between the filled in one and the open one. Oops. So here's the green branch of my function. So it goes from here to here. And then I guess I'll do my last part in red pen. So for x is greater than or equal to 1. So again, we're allowed to have f at 1 now for this, because 1 is greater than or equal to 1. Substitute in here, 1 squared minus 2 times 1, negative 1. So 1, negative 1, there's a filled in dot. And then f at 2 is 2 squared minus 2 times 2, which is 0. F at 3, 3 squared minus 2 times 3, so that's 9 minus 6 is 3. 4, let's see if it fits in. It's going to be 4 squared minus 2 times 4. So 16 minus 8 is 8. No, it's just off our page, but we can draw in this part of our piece of our function. So there's our piecewise function drawn in. It's got the yellow, the green, and the red piece. So then it wants us to evaluate two limits. The limit as x approaches -1. So you can see as x is approaching -1 from the left, our curve is approaching -1. As x is approaching -1 from the right, also approaching -1, so exists and is actually equal to -1. How about the limit as x approaches 1, so +1? From the left, my curve is approaching 1. As I approach 1 from the right, I'm in the red piece, I'm approaching -1. So since the left and right limits don't match, then the limit does not exist. So instead of an equal sign, DNE does not exist. Okay, and then C, it is said that the graph of y equals f at x is continuous at x equals -1 and discontinuous at x equals 1. What do you think is meant by this? Okay, so as you can see, there was in this green branch an open hole that was filled in by this closed part here. So we've got a continuous portion of the graph here, no holes or gaps. So at right here is where we're talking about, when we talk about continuous, it just says at x equals -1. So are we continuous here? Yes, there's a filled in hole there, so we're continuous. Discontinuous at x equals 1. So here's x equals 1. There is a gap, okay? So here's our gap in between here and here. It's not continuous, okay? So that's what discontinuous means at x equals 1. All right, so success criteria as you're working through the practice for this is that you can determine the limit of a function from its graph and determine whether or not the limit exists. You can determine one-sided limits from a graph, so the limit from the left and the limit from the right. You can sketch a piecewise function. That's going to be what I really need you to work on here. It's probably the most challenging part from its defining equation, and then use the graph to evaluate limits if they exist. You understand what an open hole versus a filled-in hole means on a graph. And you're starting to understand the meaning of the terms continuous and discontinuous. All right, bye guys.